Gathering in Harrisburg today, it looks like. Thanks for joining us all. Not boiling water anymore, Hillary. Way to go. That sounds like fun. Well, we're going to get underway here as a few more people are joining us. We had a record number of registrants today for today's webinar. My name is Jon Laughner. I'll be your moderator from TOPCORP and representing TOPCORP today from Penn State. Thank you for joining us all. Dr. Kerry Sublette from the University of Tulsa, retired, is here with us today. And you're going to really enjoy his presentation. Before we get into that, I'd like to make just a couple comments. And number one among that is Dana Olendijk is our technical and organizational expert. She's always with us on these webinars. If you have any kind of a technical issue, as we'll attest to here privately among us, that we had a challenging start and it all worked out fine thanks to Dana. If you have any technical problems or have a question that needs some kind of assistance from the webinar side, please give Dana an email or a chat request and she'll be right with you. We have, let's see, maybe just go to the next one, Dana, please. And just, this is kind of as a refresher for many of you, and that is that you're familiar with TOPCORP. TOPCORP does training for state, federal, and Canadian regulators, and saying that we do it internationally as well. So we have an international reach of the training that we do for regulators and policymakers as well at many levels of government, local to federal. And many of you have taken part in the TOPCORP training in person, and we certainly appreciate that. And if you're with us today, thank you for joining us again. Next, Dana. We have, if we go back just to show our supporters, we have a whole list of supporters, both NGOs, industry partners, environmental groups that are supporters of TOPCORP and provide the bulk of funds that allows the TOPCORP program to take place. And many of these people have been with us since TOPCORP's inception about 2013. And we appreciate their support and their willingness to be partners with us in this training, and appreciate that they see the value of the TOPCORP program. And next, as kind of a lead up to today's webinar, if we have time at the end, Dr. Sublette will take questions. So if you would enter those in the Q&A pod, specifically the Q&A pod, and save the chat pod for our introductions and anything that maybe Dana needs, you need some of Dana's assistance with. So as we go through the presentation, use the Q&A pod down at the bottom of your screen to enter any questions. And so with that, if we'd advance to and just as a note, the webinar will be recorded, and you'll get a link later that if you have any colleagues that perhaps missed this, or you'd like to review something that's been presented, you'll get a link to today's webinar that you can back and look at. Now we will keep this to an hour, so I'll pass this on to Dr. Sublette here just quickly. And with that, the next slide, Dana, introducing to you to Dr. Kerry Sublette. Kerry's going to talk about the remediation of orphan well sites. Success is in the science. Several of us had the opportunity, and maybe some of you in the audience today had an opportunity to see Dr. Kerry and see his presentation, some of the work that he has done in the past, but several of us got to see his presentation at the IOGCC conference this past November, which is how we made a connection with him and enjoyed the presentation, and he'll be doing something very similar to that today. And so with that, Kerry Sublette, University of Tulsa, thank you for being with us. I'm going to turn it over to you, and just for the audience's note, Dana is advancing the slides for Kerry, so there will be that, that awkward asking for a slide change with every slide. So just so you know, it's not it was more a problem on our end and not somebody else's. So just makes it a little bit more awkward, but it'll be just fine. So thank you again for joining us. I'm going to turn it over to Kerry Sublette. Thank you, Kerry.
Okay, thank you. Can everybody hear me?
Yes.
Okay, great. Thanks for that introduction, John. As John said, the title of my presentation today is Remediation of Orphan Well Sites, the Successes in the Science. And I think this is a very timely topic, especially with the money that's going to be flowing around for orphan well restoration in various states and various federal jurisdictions as well. Can we go to the next slide, please? Thank you. I probably don't need to tell this group about, what the advantages are or what the need is in terms of plugging abandoned and orphan wells, preventing emissions of greenhouse gases like methane and CO2, as well as VOCs, preventing surface discharges of brine and hydrocarbons, and preventing groundwater contamination. But when we plug the well, we get these, these benefits, but we're not finished because there's more to do. Can I go to the next slide? After the well has been plugged, we need to restore the site, and there's several elements of that. Probably the most obvious is that there's going to be a lot of tanks and piping and separators and things like that that need to be removed and disposed of. In some cases, that can be complicated by the possible accumulation of norm in some of this equipment. We're going to have concrete pads that need to be disposed of, and many times they can simply be buried. Next slide. But after plugging the well and after removing all the surface equipment, there is still a lot to do, and that's the subject of my presentation today, and that is restoring the site. Restoring the site because the site has more than likely been damaged by release of produced fluids like hydrocarbons and produced water, as well as there may have also been other types of activities on the site causing soil compaction and other impacts to the soil that are going to inhibit revegetation. Excuse me, I'm suffering from allergies today. But I want to confine most of my talk today to these produced fluids that have been released, and one of them we'll talk about here are hydrocarbons. And we won't say a whole lot about hydrocarbons because hydrocarbons are the easy part. We find hydrocarbons in these abandoned sites in different ways or in different locations and in different states. We may find highly weathered material as pictured in the diagram, or excuse me, in the picture that you see on this slide. And frequently that can simply be excavated for disposal. But under that asphaltic type of material, we'll likely see liquids as well. And if they're near the surface, then bioremediation is a excellent technology for degrading those hydrocarbons or taking the hydrocarbon concentration down to the point that it's not going to be detrimental to vegetation or soil biota. And that basically means stimulating the microorganisms or bacteria that are already there in the soil by providing aeration and moisture and nutrients to stimulate biodegradation of those hydrocarbons. If the hydrocarbons are deeper, then bioremediation becomes more difficult because it becomes more difficult to get the aeration down there and to get the oxygen down there and get the nutrients down there. But we have excellent technologies out there like in situ chemical oxidation that are very good at oxidizing these deeper hydrocarbons and converting them to innocuous materials that aren't going to cause us any problem. I do have one word of caution on here is there are a lot of different kinds of oxidants that are used in situ chemical oxidation. And many of them, unfortunately, are sodium-based, and you'll see why that's important in a few minutes. But sodium-based oxidants can cause more problems than they cure. And just a little word of caution here that if you are going to use ISCO, use an oxidant that you're going to be injecting into the subsurface, there are several calcium-based oxidants that are available on the market that are much preferred. And again, you'll see why that is the case in just a few minutes. Next slide. Now, the other produced fluid that is released at a lot of these sites and found to contaminate these historic sites where these wells are being plugged is brine or produced water. And I've got it highlighted here because that is the biggest problem. Especially in the later stages of production, these wells were producing probably many more times the volume of produced water that they were oil. So brine or produced water is very likely to be the dominant fluid that's been released at this site. And therefore, for historical releases or historical sites, brine contamination in the soil is the #1 obstacle to restoring the productive value of that land. After we've done the plugging, after we've removed the surface equipment, after we've taken care of any hydrocarbon spills. And what's worse is that brine, unlike hydrocarbons, brine is very highly mobile in the environment. Anytime water comes in contact with brine, it's going to move with water. So it's very likely at a historic site to have moved beyond the site of the original release. And that's both horizontally and vertically. So another reason that brine is one of our biggest problems, if not the biggest problem, in terms of restoring some productivity to the soil at these sites. Next slide. So just a little primer here, if you're not familiar with the problems that brine causes, the release of any sort of produced water or brine to soil causes basically 2 types of problems. One, it increases the salinity of the soil, and increasing the salinity of the soil results in an inhibition of plant growth, sometimes to the point that plants are going to be basically killed. They basically die of drought. They're not dying because there's anything inherently toxic in that brine. Is primarily sodium chloride, which is not toxic. But however, a high concentration of this material in the soil gives the soil moisture, soil water, a very high salinity, which results in an osmotic imbalance between the inside and the outside of the cells and plant roots, resulting in the loss of water from plants to the surrounding soil. So there may be a lot of water in the soil, but if the salinity is too high, the plants can't get that water and they die of drought. And the same thing can be said of soil biota for the same reasons. Now, the other problem that we have with a produced water spill or a brine spill is sodicity. And sodicity means an excess of sodium in the soil. As I said, the primary component of this produced water is sodium chloride. So a release of produced water into the soil results in a lot of sodium entering the soil. And the result of that is a destruction in soil structure. The reason for that is because clays in the soil, clay platelets, are held together naturally by calcium ions in the soil. And when you flood the soil with sodium, a high concentration of sodium can cause that calcium on the clay particles to be dispersed, and it replaces sodium at those cation binding sites on the clay lattice. And the result is that the stacks of clay lattices basically disperse. It's kind of like you can kind of think of a naturally occurring clay particle like a loaf of sliced bread in a cellophane wrapper. And everything's being held together here by calcium. But if you inject, or if you flood the area or flood the soil with sodium, it's like taking the cellophane wrapper off of that loaf of bread and just throwing the pieces up in the air and letting them stack. So basically, you've converted large particles to much smaller particles, which severely inhibits water infiltration into the soil and results in what we frequently call a hard pan, excuse me, in which the water cannot penetrate the soil because the clays are packed so tightly that water cannot infiltrate. The result is that when water does fall on the site, it just runs off the site, and that results in erosion. So we've got those two issues that cause damage when brine spill occurs: excess salinity, excess sodicity. And both of these need to be addressed if we're going to restore the productivity of that site. And by the way, a little bit earlier, I said that if you're going to do ISCO, use a calcium-based oxidant, not a sodium-based oxidant. I think maybe you see the wisdom in that now. If you introduce a lot of sodium with your oxidant, you're going to increase sodicity, and you might oxidize the hydrocarbons, but you're going to create more of a problem for yourself that you're going to have to solve to regain soil productivity. Next slide. Now, I'm not seeing a little bit of the bottom of my slide here. I'm sorry about that, but salinity and sodicity effects are dependent upon the mass of the salt that gets spilled. And that mass is equal to the total salt concentration, or the TDS, or total dissolved solids, and the volume of brine, or volume of produced water that's released. So if you're in an area with high TDS produced water, then you're more likely to have more serious problems with brine in terms of excess acidity and salinity. And this is just a map from USGS with TDS, average TDS concentrations in various producing areas around the country. So you can see the more you're in the yellow and the red here, the more likely you're going to have severe problems at abandoned sites because of release of brine. Next slide. So I've just got a series of pictures here. Probably many of you have seen these kinds of things before, but this young lady right here is at an abandoned well site, and as you can see, there have been releases of produced water and brine on this site, resulting in the death of vegetation. You can even see some dead trees here as well. And what you can't really see is the excess acidity in the soil, but you can see that soil is pretty tightly packed. Next slide. Similar situation here, not as severe. There is some vegetation growing, but definitely there's been an impact of vegetation because of the release of brine. Next slide. Again, same situation here. Next slide. And here in this slide, you can see to the left of the wellhead there, you can see salt crystals on the surface there, resulting from the release of brine at the site. One of the things that makes the remediation of brine spills so difficult is the fact that brine moves up and down vertically in the soil. And it's in response to wet-dry cycles. When it's wet, it moves down. When it's dry, it moves up. And when it moves up to the surface, the water can then evaporate, leaving the salt crystals that you see here in this photograph. Next slide. And I think this is the final photograph. This is an older site, and as you can see, after the vegetation has been killed, erosion has been going on at this site for quite some time. Actually, I think there's one more slide. Next slide. Yeah, this is a brine scar in Oklahoma. This particular brine scar, for example, is visible in the aerial photographs from 1937, so it is quite old, emphasizing the facts that these brine releases, once you kill the vegetation, it starts to erode. It's not going to remediate itself. There is no natural attenuation of brine impacts like this. Next slide. So I want to talk about the brine remediation and what are some of our options are. But there are a lot of misconceptions out there that I run into all the time that I want to address head on before we get into the how-to. First of all, you cannot destroy or degrade salt. The only thing that you can do is move it, and we move it with water, and we move it toward a point of collection, or we can disperse it over a wide area at a low concentration that's not going to be impactful to vegetation. Contrary to what some vendors will tell you, there are no microorganisms that will eat salt. There are also no amendments out there that will permanently bind salt. Again, you may have heard a vendor try to sell you on this concept. There are ion exchange agents that can be worked into salt spills that will temporarily bind some of the sodium and chloride components. But these ion exchange agents, just like all ion exchange agents, are labile, and that material will eventually be released. So there is no magic bullet here for binding up the salt and keeping it from affecting revegetation or soil productivity. There is not going to be any remediation of brine spills without water except for dig and haul. So any kind, if you're not digging it up and disposing of the brine contaminated soil, any remediation is going to require water. You'll see why in a moment, but that water has to come in contact with the salt, and then that now salty water needs to be conveyed by appropriate drainage to either a point where it can be collected for disposal, or as I said earlier, dispersed and diluted over a wide area to a point it's not going to cause any problems. And again, despite what some vendors will tell you, there are no magic potions for fast results. There is absolutely nothing that you can spray on a brine spill, especially a historic brine spill, that's going to remediate that site. And if anybody tells you that, they're not being truthful with you, whether they know it or not. A popular response to a brine spill, I can tell you in Oklahoma and probably all over the country, is just to spread a little gypsum around, maybe scratch the ground a little bit and then walk away and assume that that's going to be good, and it is not. It's a recipe for failure. Short-term revegetation is not success. Long-term beneficial revegetation is the measure of success. I can't tell you how many times I've seen companies, quote unquote, remediate a brine spill in Oklahoma. And they do some of the things that you should be doing to try to do in situ remediation and driving the salt down in the soil profile temporarily while they get some sort of rapidly growing grass to grow. But then when it gets warm, and remember the wet dry cycles and capillary suction bring brine back to the surface, it brings it back up into the root zone and kills that vegetation off, and you're exactly where you started. So the definition of success in remediation of a brine spill is to reestablish beneficial vegetation in the long term. Next slide. Okay, so let's talk about how we address historic brine spills. First of all, site characterization. And as I've indicated in bold here, if you don't take the time to understand the distribution of salt, both on your site and off your site, then anything that you do to try to remediate that site is just going to be guessing. And what you don't know is going to come back to bite you. So how do we determine where the salt is? And I'm talking horizontally and vertically here. The best course of action for a historic site consists of two steps. The first step would be some sort of non-invasive geophysical survey that measures subsurface conductivity. And there are a couple of ways that we can do this. One is to use electromagnetic induction profiling. And I'll show you one of these instruments in a moment. That basically there's several different instruments that can measure subsurface conductivity. They have different depths of penetration or investigation. They provide you with a cumulative measure of the distribution of conductivity in 2 dimensions with some limited information, as you'll see, about the depth of the contamination. So you'll get a 2-dimensional picture with a quasi 3-dimension thrown in. The next, and unfortunately more expensive, is to do a resistivity survey. And a resistivity survey measures subsurface conductivity versus depths in slices in the earth, as you'll see. And then no matter what type of geophysical survey you use, you follow that up by soil coring and lab analysis. And that's going to ground truth your geophysical data and give you precise measurements of salinity and sodicity. And the coring that you do to collect these samples is going to give you information on shallow stratigraphy that's going to be useful to you in remediation. Next slide. So for example, doing electromagnetic induction profiling, you see an EM31 on the right-hand side here. And basically what's happening with this instrument is you're inducing an electromagnetic field at one end of the instrument that induces a current to flow in the subsurface, and then you measure the secondary electromagnetic field generated by that current flow with the other end of the device. And so the amount of current that's flowing then can be measured and is proportional to the conductivity or the amount of salt in the subsurface. There are 2 modes of operation here, a horizontal and vertical dipole. And I've just shown you on the left-hand side here the contribution of measured conductivity to the overall signal that the instrument produces. So by operating it both in a horizontal mode and a vertical mode, you can get a little bit of information about depth of contamination, because you can see in the horizontal mode, it's more sensitive to shallow contamination, whereas in the vertical mode, it does penetrate deeper into the soil subsurface. Next slide. From these measurements, you can generate a 2-dimensional contour map like this one of conductivity. And then when it comes time to basically ground truth this data, this map will guide you into where to take your cores to validate this data and determine, if you're doing an EM survey, determine precisely where that subsurface salt is in the coring operation. Next slide. These guys are doing a resistivity survey now, and basically what they're doing is putting electrodes in the ground and applying a current and measuring applying a electrical field and measuring the current that flows. The distance between the electrodes will determine the depth of penetration or the depth at which conductivity is actually being measured. Next slide. The result is that it generates maps like this. Each one of these maps represents a slice in the earth. So you're looking at basically taking a slice, and here we're looking down around 70 feet or so. And in that slice, along that line, it's measuring subsurface conductivity, and you can see that represented by the scale to the right-hand side. So in the upper slice, for example, you're seeing that the highest conductivity has been identified in the right-hand part of the line there. And you can see it's at a depth of about, the bottom of it is at a depth of about 25 feet or so. But just gives you an example of how to use this data to determine depth of contamination. Of course, you can then combine several of these slices to actually produce a three-dimensional map of conductivity, subsurface conductivity at a site. Next slide. And then the next thing we do is to ground truth that data. And if we're using EM, that's going to establish for us exactly what that vertical distribution of salt is. It's also going to allow us to correlate geophysical signal with actual lab measured salinity, whether we're using EM or resistivity. Next slide. Now, one thing I always recommend to folks is to just remind you or tell you, if you're not familiar with agricultural laboratories that are associated with land-grant universities, will provide salinity analysis basically at cost. So for example, in Oklahoma, we use Oklahoma State University. You can see the analysis that you're getting on this particular soil, everything from EC to actual cation anion analysis, the sodium absorption ratio, which is a measure of sodicity, and you're getting all this information for $55. If you go to a chemical laboratory, you can get these same analyses done, but it's going to cost you a whole lot more. So my experience is find a good ag lab. You get a lot more information for a lot less money. Next slide. All right, so let's suppose we've characterized the site then. Now we're going to be thinking about remediating the site, and there's two things we think about, either doing ex situ or in situ. Ex situ means simply it's dig and haul. We're going to excavate the contaminated soil and we're going to take it for disposal. In situ means we're going to treat the spill right there in place. Now, for most of these historic sites, you're going to have two types of brine impacted areas at these historic sites. In many cases, you're going to have pads, old pad and tank battery areas, or you may have areas that are very highly eroded. And in these areas, frequently the original upper soil profile is gone. And in these cases, ex situ or dig and haul may be your only option. However, one aspect of this that frequently gets overlooked is that the quality of the replacement soil, if you do excavation, is extremely important to the success of the restoration of this area. Without proper attention to chemical, physical, and biological properties of this replacement soil, you can end up creating an ecological island that, in terms of vegetation and vegetation support, is going to look and act different from the surrounding area for many decades. It's greatly to your advantage to try to match that replacement soil and the stratigraphy of that replacement soil as much as you can to nearby productive soil to get a productive restoration of the site. Next slide. Now, there are also, as I said, there's basically two types of brine impacted areas at these historic sites, and then we could probably add a third for some gradient in between the two. But the other type of soil, other type of spill that you're going to find at these sites are going to be areas where there has been a brine release, and through runoff and leaching from that primary brine spill, other surrounding soil has been impacted. There's an example that you see, and this is a Google Earth photo on the lower left, and the I'm sorry I can't be pointing here, but at the junction of the lease roads there, you see that white area that's actually a tank battery as well as a a well and pump jack. Just to the right of that is a white area that is a brine release that took place from a ruptured line. And then with time, the brine was carried down gradient. You see another smaller white area, and then off to the further out to the right, a kind of light area out there that is going downhill from the original spill. And you see the results of EM survey on the right-hand side. And as you can see, that original spill resulted in the transport of salt away from the original release site, contaminating these other areas. And that is very common in these historic sites. You know, and what's interesting too, in this particular case, you see that kind of light area off to the right there. If you stand on the hill and look down there, if you're inspecting the site, looking down there, Google Earth is showing you that there's an impact to vegetation, but if you're standing on that hill, you can't see it. Unless you go down there and walk around, then you can kind of get an idea that the vegetation is kind of thinned out down there. But by doing an EM survey, it definitely confirmed that salt has moved down to, you know, all the way down the hill to that spot. Now, in many times, the original productive soil, or what was productive, and the soil profile in these areas where brine has been transported off site is generally intact. And if so, then in situ remediation is preferred. This because in situ minimally disrupts the soil integrity, and it by and large results in more productive plant communities compared to pre-spill conditions. Next slide. So in situ remediation of a brine spill is all about water, calcium, and drainage. Next slide. So this just represents some of the normal pathways of the movement of water in the environment. And we can use what we know about the movement of water in the environment to basically guide us in how to do in situ remediation. Thank you. Because as I said before, water is going to be critical to doing any sort of brine spill remediation other than dig and haul. So water has to come in contact with the salt and convey that salt to a place where it can be collected or dispersed over a large area for dilution. So that means we facilitate that contact by doing things like ripping, tilling, and using bulking agents like organic matter. We have to have a water source. Sometimes that can be rain, sometimes not. We have to take measures to maximize the effectiveness of that water, increase its penetration into the soil, prevent its evaporation. And then we have to worry about where that leachate is going to go, as I said, whether we're going to collect it or whether we're going to be able to disperse it over a large area without impacting groundwater. Next slide. The role of calcium is to reverse that sodic reaction that I talked about earlier, where an excess of sodium causes clays to disperse. And that's represented by the little seesaw you see on the left-hand side. If you've got an excess of sodium compared to things like calcium and magnesium, then you're going to have a dispersed soil. But we can reverse that by now flooding the site with calcium ion and displace the sodium again with calcium, and that allows the clay particles to reagglomerate. Next slide. We know how much gypsum to apply, or excuse me, if we're using gypsum as our calcium source, and that's what I would recommend with some caveats, as you'll see in a moment. As long as we know what the sodicity is as measured by the SAR or ESP, and we know what the cation exchange capacity of the soil is to measurements that are easily acquired, it's easy to come up with gypsum application rates using the data like you see on this chart here. Next slide. Now, all gypsum is not created equal. Particle size is very important. You're seeing in the photograph here, someone tried to use broken up wallboard as the source of gypsum and the remediation of a brine spill in Illinois. You know, I've seen it all out there. But what you need is a small particle size because gypsum is only sparingly soluble in water. So the particle size is extremely important to mobilizing the calcium from that gypsum so that it can enter into that reaction with the dispersed clays, displace that sodium and reagglomerate those clays. What I always recommend, for example, is what's called solution grade gypsum. It's a very fine gypsum flour. It's 400 mesh. Next slide. Now it's important to get that calcium where it's needed. Gypsum is only going to be effective to the depths at which it's incorporated into the soil, which is the major reason why I said before that scratching the soil and scattering gypsum is a recipe for failure. Because the effect that you're going to get from that gypsum is only going to be in the top few centimeters of the soil. You've got to work that gypsum down into the soil. Next slide. All right, so let's kind of summarize here and amplify. The remediation of brine impacted soil is going to be a major component of restoration. And as I've emphasized here, failure to adequately remediate brine damage is the #1 source of landowner complaints in orphan well restoration programs. Next slide. For example, here is a newspaper article. This is from 2021 about a program in North Dakota where they were using CARES Act funding for plugging and restoration of abandoned wells. And as you can see here, the landowners are very unhappy because the remediation is incomplete, as indicated in the circle to the right. Landowners complained that cleanup was at times incomplete. The contractors removed gravel pad, did not address contamination apparent in the surrounding land. Next slide. And if you go to the next slide, you see what is it they're complaining about? Saltwater impacts. So that is the #1 problem, and that's the one that the landowners are going to judge you by when it comes to remediation and restoration of these types of sites. Next slide. When ex situ is required, again, I want to emphasize the importance of the quality and management of the replacement soil. If the original soil profile is undisturbed, then in situ treatment will conserve a valuable resource, and that valuable resource is the topsoil, even though it's been impacted with salt. That topsoil contains the native microbiota of that soil and the native seed bank, and the restoration of that soil is going to give you the greatest probability of restoring productivity. I had an interesting comment from a large North Dakota farmer one time that he told me that depending upon the crop, that for him, the productivity of restored land's got to be 75 to 95% of the unimpacted land, if we're in an agricultural area, to be economically viable for him to farm. So if you restore 50% of the productivity of an agricultural land, that 50% productivity sounds like, well, you're getting something. But at 50%, it doesn't make it economically viable for him to go to the trouble of trying to produce that. So I thought that was a very interesting point of fact. Next slide. So in situ treatment is typically going to take 2 to 3 years. Everybody needs to be patient when it's done properly, but it will give a superior result to dig and haul at a much less cost and with much less environmental impact. Next slide. And what environmental impact am I talking about? Well, here's a little calculation I did for a client some time back, looking at the environmental impacts of a dig and haul operation. In this particular case, they were going to excavate 12,000 cubic yards of soil. It had to go 75 miles to the landfill, and it was 25 miles to a site of makeup soil. So that corresponded to 2,100 truckloads of soil that had to be moved. and that was 38,000 gallons of diesel that were going to be consumed. So using EPA estimates, you can see here the amount of CO2 or greenhouse gases, and pollutants like VOCs, carbon monoxide, NOx, and small particles that were going to be released into the atmosphere in terms of emissions. But then we had nuisance and hazards like noise, increased traffic and nuisance, impacts to roadway infrastructure from heavy vehicles, dust and debris, risks of road accidents, on-site hazards. And then we got additional considerations for all that heavy equipment moving around in the area, damage to existing vegetation, soil compaction, damage to trees if they're present, the possibility of on-site spill control. So dig and haul, my point is simply that dig and haul is not a clean operation. Yes, you can remove the soil and you can take it to a landfill, but you have created an environmental footprint by doing so, as well as taking up landfill space. So if you can do it in situ, you're much better off. Next slide. So in conclusion, there is no one-size-fits-all formula for doing in situ treatment, but it is not rocket science. It's just plain agronomy. And the point that I can't make enough is there are no magic potions. The internet is full of products that people would like to sell you and tell you that all you have to do is spray it on an impacted site and magic things are going to happen. Well, magic doesn't happen in this world. When it comes to a source of calcium, again, there are a lot of sources of calcium that people will like to sell you. But there is no need to buy an expensive source of calcium. That fine particle, gypsum, that I was telling you about a few moments ago, is only 6.5 cents a pound. So it is the most cost-effective material to supply gypsum, to supply calcium in these sites that is available. Next slide. So that concludes my presentation, and it looks like we have a little bit of time for questions. I'm happy to take questions. You see my email address here. If you would like a PDF copy of this presentation, I'm happy to send it to you. If you just send me an email or send me a text at my phone number that you see there. And as I said, I'm happy to take questions.
Thank you, Kerry. Very interesting. And again, our number of participants shows that. And thank you for the information. Thank you for the presentation. It's quite interesting. And as you mentioned, there are a couple questions and we still have a few minutes. So with that, Dana, do you want to say something about this?
We have a poll. We'd appreciate you taking a minute to let us know how you enjoyed this presentation. Thank you.
Thanks, Dana. Thanks for putting the poll up. Yeah, we appreciate the feedback for all of you that would take a couple minutes to do that. And now with the questions, and Kerry, I'm going to read this, and I think I've got some terms here that I'm not familiar with. What if your orphaned well is located on a calci pad and doesn't show signs of brine release, in parentheses, since there is little to no vegetation growth? Would you approach an assessment with an EM to spot potential issues?
Okay, the word you're looking for there is caliche, I'm sure.
Ah, thank you.
Caliche is, if there's no evidence of any surface damage, yes, doing an EM survey, I think would probably be a very good idea. One thing about caliche is it's highly fractured. And if there has been a brine release in the past, it has probably been conveyed through these fractures into the subsurface. And frequently there will be some sort of impermeable layer down there that may stop that vertical movement and allow it to accumulate in the subsurface. Now, if that's the case and it is too deep for capillary suction to bring it to the surface to inhibit any vegetation, And if it's isolated from groundwater, this may be a case of just leave it where it is. But until you do a site characterization, you don't really know what you're dealing with. I hope that answered the question.
The next question is, how effective is gypsum application for deep brine contamination? And can it be applied deep enough?
Well, it depends on your definition of deep again. My definition of deep is the brine contamination shallow enough that it has the potential through capillary suction to be brought back to the surface and back into the plant root zone. And what that depth is depends upon the types of soil. A very high clay soil, for example, has a lot of capillary rise potential. So salt that could be as deep as 10 or 15 feet, or even more in some cases, still might have the potential to rise back to the surface and get into the plant root zone. Take the other extreme, if it's a more sandy soil and that brine is down, say, at 3 feet or so, it's never going to be back to the surface into the root zone unless you've got plants there with the deep root systems. So those are the kinds of things that you have to consider. What kind of vegetation is desired? What kind of root structure does it have? What kinds of soil structure do you have and soil texture do you have? That can determine for you how much of an impact deep salt might have on revegetation. Of course, we've got the other thing to worry about too, is potential impacts on groundwater. So that's another consideration. How deep is groundwater? Is it fresh groundwater? How much rainfall do we get? What's the evaporative index? Is it likely that salt will ever reach groundwater? So a lot of questions have to be answered, which means to answer those questions, we have to know a lot about the site.
Did we lose audio?
Can you hear me?
There, nope, there you are. Yes, thank you.
I'm sorry. No, someone just asked if you could put the last slide back up.
Okay, I'll leave that to Dana and we'll move to the next question, Kerry. How exactly would in situ remediation of a brine spill work? And for example, a spill that might be up to 30 feet deep.
Well, for a spill that's up to 30 feet deep, again, I'll refer the questioner back a little bit to the question we answered before. It depends on what the possible fate of that salt is and how close to the surface it is. If it's sufficiently deep, the capillary suction will not bring it back up into the root zone, then we don't need to do anything about it unless it's a threat to groundwater. But in some cases, I mean, I'm thinking extremes here. Again, I hate to sound like a broken record, but we really need to know what the stratigraphy of the site is, the soil texture, where the brine is. The shallow brine is going to have the highest risk to surface vegetation. If I could just kind of imagine a scenario where I had a site with contamination all the way from the surface, from the surface all the way down to 30 feet. This might be a situation in which we have to do dig and haul, or perhaps we can remediate the top, say 3 feet of the soil using an in situ method, but then we might have to excavate that and put down a impermeable clay layer and then put that soil back in the stratigraphic lifts that we removed it from. So I'm sorry, this is a complicated question that I'm trying to answer in just a minute here, but hopefully that gives you kind of an idea. But once again, it all depends on the characteristics of the site. And just remember that there's always two things. We have to know the characteristics of the site to predict what's going to happen to that salt. And there's two things we want to protect. One is the root zone and the other is groundwater. So what can we do to protect the root zone and protect the groundwater? It could be a combination of in situ, ex situ. It could be a combination, as I said, of in situ. Then we excavate, put down a barrier, put the clean, productive soil back in, and therefore we've isolated the salt from the surface. But again, we then have to still think about groundwater. As a long-winded answer to a complicated question.
Yeah. Thank you. We do have a couple more minutes and a few more questions, so let's try to, we'll squeeze a couple more in maybe.
Okay.
So, is lime an appropriate source of calcium?
Lime can be used as a source of calcium, but you have to be careful because it's going to increase pH. And depending upon what the buffering capacity of your soil is, you can raise the pH to the point that the pH alone will be inhibitory to revegetation.
Okay. Can you provide any field screening suggestions for interim remedial actions by excavation?
I'm sorry, can you repeat that?
Sure. Can you provide any field screening suggestions for interim remedial actions by excavation?
Oh, yes. Well, let me do this very quickly. You can buy portable EC meters for about $100 that just fit in your pocket to allow you to measure the electrical conductivity of a solution. What solution am I talking about? Going out into the field, taking a soil sample, mixing it with distilled water, and measuring the conductivity. And if you establish, you can establish a fixed method in which you're doing that, a certain volume of soil, a certain volume of water, and then also sending that same soil sample off to the laboratory for an actual lab analysis. And this is site by site specific. That can give you a correlation between your measurement of the extract by that method you've developed and the actual salinity of the soil that you can use then to screen in the field.
Okay. How about one last question? Are there types of trees or vegetation that can be planted on a brine affected area to uptake or remediate the salt?
Thank you so much for that question. The best I have ever seen, yes, there are plants that do withdraw salt from the soil, but the question is two things. How much salt do they withdraw? Usually on the order of maybe 1 or 2% per year. So you can see it's an extremely slow process. But then if that's going to result from the removal of salt from the soil, that vegetation has to then be harvested so that it doesn't die and drop back down on the ground and decompose and release that salt back into the soil. So that type of phytoremediation for brine spills is extremely takes an extremely long amount of time and is very inefficient.
Very good. Well, thank you, Kerry. Number one, thank you for the excellent presentation and the informative educational value that you provided today. And from our participants, it's obvious by the number that we had and the types of questions that we had that this was of great interest to a lot of people. So thank you again, Kerry, for participating and being a part of this. We're sure glad that we ran into you at the IOGCC and appreciate your time with us here today. So from we as TOPCORP, from our TOPCORP team at the University of Texas at Austin, the Colorado School of Mines, and the Penn State University, we thank you all for attending. Look for an email that will provide a link to this presentation that you can share with your colleagues or review yourself. and an email. We try to do a TOPCORP webinar every quarter, and you should see a notice for another one coming up very soon. So until then, we'll look forward to seeing you at our next webinar. Thank you all for attending. Dr. Sublette, thank you again for your presentation, and we look forward to seeing you all again.
Well, thank you for the invitation.
Thank you. So long.